Okay, can you see my screen? Can you hear my voice?
Yes, Doctor.
Yes, Doctor.
Okay, thank you for the response. Okay, so previously on Sunday and Monday, we have learned up to this topic, which is the encoding process. So encoding process is part of the formatting process, which consists of three processes that we have learned in class. The first one is sampling, where we take sample of the analog signal. Okay, we convert a continuous time signal into discrete time signal. So that is the first process, which is the sampling. So sampling process produce PAM signal, pulse amplitude modulation signal. Okay, and then we learn that after we sample the signal, we do the quantization process, the second process. So the quantization is the process of rounded up the sample value to the nearest quantized level. So that is for the quantization. So after quantization, we produce a PCM code word. Okay, so we produce after quantizations, we produce a quantized signal that has been which is based on the sample signal that has been rounded up to the nearest quantized level. So now during the quantization process, we have rounded up the sample value to the nearest quantized level. So now the quantized level is calculated based on the number of bits used in the system. Okay, so we have learned how to calculate the number of quantized level, and then we have learned about how to calculate the resolution, which is the step size. Okay, and then we also have learned about how to calculate the dynamic range. So dynamic range is the number of step size. Okay, the number of step size or the number of resolutions within the highest and the lowest quantized voltage. Okay, so that is for the quantizations, the second process. Now we want to learn about the third process. Okay, so the third process is assigning the quantized values with the specific code word. Okay, and what we will produce at the end of the encoding process is the pulse code modulation code word, okay, PCM code word, which is in the form of logic 0 and also the logic 1, okay, which is this topic. So before we proceed with the encoding topic, maybe I can summarize what we have learned during the formatting process. Okay, so initially we have the analog signal. Okay, we have the analog signal, which is V of t. So this analog signal is continuous over time. Okay, and then we do the sampling process. Okay, so the sampling process, we take samples by samples. Okay, we take samples, another samples. Okay, so this is we have changed from continuous time signal into a discrete time signal. Okay, and the sampling time is defined as TS, which is a sample time, TS, 2TS, 3TS, and so on. Okay, so this is what it is known as the pulse amplitude modulation signal. And we have learned that the way we want to sample is based on the Nyquist theorem. So the sampling rate must be more or equal to 2 times the highest input message frequency. Okay, so this is the Nyquist theorem. Okay, And Nyquist said that we cannot sample less than 2 FM, otherwise it's going to produce aliasing, which is of overlapping of sample signal in the frequency domain. Okay, so if aliasing happens, means that it's going to cause a big problem that the receiver will be unable to differentiate between one sample and another sample. Okay, so we need to sample at least 2 FM, 2 times the highest input message frequency. Okay, and then after this, you see that our sample values has infinite range of values, which is difficult for us to do the signal processing. Okay, so since we have infinite sets of values, okay, infinite variation of values for the sample values, so we need to round it up the values to the nearest levels so that easy for us to process it and to make it as digital signal. Okay, so the next process, the second process, it is what we call as the quantization. Okay, so quantizations, we rounded up the values. Okay, quantization is the process of rounded up the sample value to the nearest quantized level. Okay, so for example, I have from minus from Q0 and then Q1, for example, Q2, and then Q3, for example. Okay, so for example, I have 2 levels. Okay, I'll round it up to the nearest quantized level. Okay, and so now when I have do the quantizations, I rounded up the sample value to the nearest quantized level so that I can reduce the variation of sample values. Okay, so the rounded up process can be either we increase a little bit of the sample values or we decrease a little bit of the sample values. Okay, so the number of levels is equal to 2 power of n, which is n is the number of bit used in the system. Okay, so in my example, I have 4 bit. That means I'm going to use 2 power of 2 bits, which is 4. Okay, so this is from my example. And you see that this quantization still in the form of voltage versus time. Okay, voltage versus time, which is not digital yet. Okay, we are still in the form of analog. Okay, so I still have quantized voltage. From here, I have learned that the resolution is the step size. Okay, resolution is the step size. And we also have learned about dynamic range. dr is equal to 2 power of n minus 1. Okay, and as I've mentioned in the class that um, uh, the more the quantized level that we have, the better would be the output signal that we produced. Okay, so if we have many quantized levels, that means the rounded up values would be smaller. Okay, if we have many quantized levels, that means we only need to round it up the values to a very small amount of rounded up values. So the more the quantized level, the more precise output signal that we can produce, which is ideally is much better. Okay. However, if we have too many quantized level, we're gonna need more bits. The more bits we use, that means we're gonna need wider bandwidth, which is not suitable for certain kind of applications. So that's why bandwidth is one of the big limitations to determine the number of bit that we need to use in the system. Okay, and then what? So the next process would be the quantization. Sorry, the next process would be the encoding process, the third process. Okay, encoding. So encoding is the process of assigning the quantized values with a specific code word. Okay, in my example, I'm using 2 bits. That means I'm gonna have 4 different unique codes. Okay, 4 unique codes, which is 00, 0001, 10, and 11. So this is actually corresponding to a decimal point of 0, decimal point of 1, decimal point of 2, and decimal values of 3. Okay, and if you see from here, from my example, I will assign the code word, okay, 00 starting from the lowest level. Okay, for example, here is 00, 01, 10, and also 11. Okay, and what happened during the encoding process? You see that I have, in my example, I have six. I have 6 quantized values. Okay, the first one here is, you see that the first quantized value here is Q2, is the first quantized values, which is this is assigned to code number 10. The next quantized element is has been mapped to the Q3, okay, level 3, and this is has the this is assigned with code 11. This is 10. This is 01. Okay, so you see that for this one is 01, this is 00, and this is 01. Okay, so I have 6 unique codes assigning to the, I have 6 codes assigned to the quantized values. So after the encoding, if you see that if I rearrange the code in terms of codes, so the first one is 10, okay, which is this one. Second one is 11. The third values is 10. The fourth, 01. Fifth, 00. And the sixth values is 01. Okay, so after encoding, I'm gonna produce this code word, which is known as pulse code modulation code word, PCM code word. Okay, this is what we call as digital data. Okay, it is in the form of logic 0 and logic 1. Okay, so this is the third process to produce the PCM code word, the encoding process. Okay, and you see that this is the explanation of encoding. And if you see from this example, okay, the encoding process we can see from these third and fourth lines. Okay, so you see that for these quantizations is the minimum values is negative 3.5 until maximum 3.5. The step size would be 1 volt. Okay, the step size is 1 volt. So this is happened during the quantizations. And during the encoding process, we assign a specific code word for each of the quantized level. So since we have 8 different levels, in this example is 2 power of, and so the number of level is 8. Okay, so that means we are going to use 3-bit, which is it will produce 2 power of 3 will produce 8. So we have 8 levels. So 8 levels with decimal point from 0, 1, 2, 3, 4, 5, 6, and 7. Okay, and if you use a binary if we convert into binary, what happened is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Okay, and in this example, we assign 0, code 0 for the lowest quantized voltage. Okay, 0, 1, 2, 3, 4, 5, 6, and 7. Okay, and if you see that the first sample, okay, the first sample is 1.3, rounded up to the 1.5 during quantizations. So 1.5 is assigned to code number 5 in decimal, which is correspond to 101. Okay, 101. The second sample is 3.6. Okay, and then we rounded up to 3.5 during quantizations. So 3.5 is mapped to code number 7, which is in binary is 111. And then the third sample is 2.3 volt. We rounded up to the nearest quantized level, which is 2.5. So 2.5 volt is mapped to code number 6. Code number 6 correspond to 110 in binary, and so on. So this is for the rest of the sample. Okay, so what happened is that we produce, at the end of the encoding process, we produce all of this code word. Okay, this is what we call as a PCM code word, which is 101, 111, 110, 100, 011, 001, and 000. So this is PCM sequence or PCM code word in the form of logic 0 and logic 1. So now, after encoding, we produce a digital data. Okay, it is not analog anymore. It is now in the form of digital. Okay, and I would like to, this example also has been learned in class for section 1. Okay, so this is actually from PCM, the folded binary code, which is in the previous example, in the folded binary example. So it is said that for PCM, the bit PCM code, the folded binary, determine the quantized voltage quantization error. Quantization error is the rounded up values. Okay, how much we rounded up the values. And the PCM code for the analog sample voltage of 1.07. Okay, so if you see that the sample voltage is 1.07. So 1.07 is somewhere here. Okay, and we rounded up to the nearest quantized voltage, which is positive 1 volt. Okay, positive 1 volt, this one. And the quantization error, the rounded up values, so from 1.07 we rounded up to 1 volt, so the error would be 0.07. Okay, and what is the PCM code for the 1 volt? Okay, what is the PCM code for 1 volt? And according to this example, it is referring to code number 101. Okay, 101, which is this one. So this is a straightforward example for the encoding process. Okay, so after encoding, what to do? Okay, we have a digital code word, and then the next process is to prepare the code word for transmission. Okay, we cannot simply transmit the code word because the code word is in the form of analog in the form of logic values 0 and 1. Okay, so if you see from here, we have this is the block diagram of transmitter and receiver. Okay, the above blocks are the transmitter, and the blocks below would be the receiver. So we have the analog input, we have the band pass filter here to select the desired frequency band, and then we do the sampling process. Okay, and then this is the process of quantizations and also the encoding process. So we produce a PCM code word, and then we convert the PCM, we convert the PCM code word into digital pulses. Then we transmit through the medium. Could you please mute?
Doctor, we cannot hear you.
We can't hear you.
Doctor, your mic is off.
Doktor tak dengar, doktor.
Okay, can you hear my voice?
Yes, doctor.
Yes, doktor.
Okay, sorry for that. I don't know, suddenly the mic is off. Sorry about that. Okay. Okay, can you hear me? Can you see my screen?
Yes, doctor.
Okay, thank you for the response. Okay, so previously I said that this is the analog signal. We have the analog input, and then we select the desired band from certain frequency to certain frequency, minimum to maximum frequency. Then we do the sampling process. The first process of formatting, sampling process. Then we do quantizations and also the encoding process to produce a PCM code word. Okay. Then what we do is we do a channel coding. Okay, we convert the code word into digital pulses so that we can transmit through the wired medium. So within the medium, from transmitter to the receiver, we have a few sets of repeater to regenerate the signal so that we can transmit at longer distance. Okay, and then uh, when the signal is received at the receiver side, so it puts into the serial to parallel converter, so to convert the digital pulses to the digital code word. Okay, so once we have the digital code word, we convert uh, to the analog signal, okay, through digital to analog converter. Then we have a whole circuit, low pass filter, and then produce the output analog signal. Okay, so this is for the baseband transmission using wired transmission. Okay, and this is also the PCM system. Okay, the same as previous. The difference is that we have a compending process here, analog compressor and analog expander, which will do the process of non-uniform quantization. Okay, remember about non-uniform quantizations where we want to have more steps for the weak signal, and in order to have a better SNR, and to have a better SNR, that means we want to reduce the amount of errors. So we have used the compending process, which will do the non-uniform quantizations. Okay, and then the rest would be the same process that we have learned. Okay, so there are a few sets of parameters. Okay, there are a few sets of important parameters which you need to know. Okay, this is very important to you. So there are three main parameters which we can measure. The first one is the sampling rate. So sampling rate, SR, or this is FS actually. This is the same as FS that we have learned, the sampling rate. So the sampling rate, or here is SR, simply as SR, is 2 times the highest signal frequency, FM. So remember, if you have many inputs, for example, you need to choose the highest input frequency. Okay, the highest input frequency would be used to calculate the sampling rate. Okay, and the unit would be sample per second or in terms of hertz. So sampling rate determine how many sample you will take in 1 second. Okay, how many sample you're going to take in 1 second. Okay, so ideally, theoretically, we need to have more samples. The more samples we have, the more accurate output we will produce. Okay, and then the second parameter would be the bit rate. Okay, the bit rate is equal to the sampling rate multiplied with the number of bit per second. So sampling rate is sample per second multiplied with number of bit per sample. Okay, so sample, we can cancel out sample, so we get number of bit per second. Okay, which is a bit per second, so we're going to produce a bit per second or BPS. Okay, so bit per second or the bit rate is actually determine the transmission rate. Okay, the speed of transmission. So this is, you can relate with the internet speed, for example. Like the Unify, for example, we have Unify 100 megabit per second, Unify 300, Unify 500, 800, and so on. So that one is actually referring to the bit rate, the speed of transmission. Okay, how many bit you can send in 1 second. So that is the bit rate. The third parameter would be the bandwidth of the PCM, okay, which depend on the bit rate and also the waveform pulse shape, either sync X or rectangular pulse used to present the data. So here you're going to see that there are two types of two ways to calculate the bandwidth. So the first one is what we call as the minimum bandwidth. Okay. Yeah. So the first one is what we call as the minimum bandwidth, which is equal to half of the bit rate, 1/2 of the bit rate. And remember, the unit for bandwidth is in terms of hertz. Okay. For example, if the bit rate is 1 megabit per second, so in this case, (500 kilohertz in this example. So this is the minimum bandwidth for PCM. Okay, so minimum bandwidth is obtained for only when we use a sync function pulse during the sampling process. Okay, so remember, this is the type of pulse that we use during the sampling process. So we remember that we have the impulse sampling and so on. So if you use a sync function during the sampling process, we're going to produce the minimum bandwidth of PCM, which is half of the bit rate, but the unit is in terms of hertz. Okay, and if you use a rectangular pulse during the sampling process, the bandwidth gonna be equal to the bit rate. Okay, so if the bit rate is 1 megabit per second, so we're gonna produce bandwidth equal to 1 mega, but the unit is in term of hertz. Okay, the unit must be in term of hertz. So normally, when we ask how much is the bandwidth of PCM, normally we will use these equations. Okay, so this is the common bandwidth that normally what we use for the PCM. The bandwidth is equal to the bit rate. The higher the bit rate, the wider the bandwidth that we need. Okay, so if you ask me, this is normally we refer as bandwidth of PCM. Okay, normally bandwidth of PCM, and previously the bandwidth of PCM minimum. So we can write this. The previous bandwidth is bandwidth minimum. Okay. As I mentioned, that normally bandwidth for the PCM is equal to the bit rate. So this is the thing that the equations that we normally use for the bandwidth of PCM. Okay. So the next example is about PCM, which is an analog signal with frequency of 40 kilohertz is sampled at sampling frequency equal to the minimum Nyquist sampling frequency. So that means it is sampled at 2 times FM. Okay. Each sample is encoded using 4 bit. So N is equal to 4. Determine the bit rate. Okay. So bit rate is equal to sampling rate multiplied with the number of bit per sample. Okay, so first of all, we need to find the sampling rate is equal to 2 times the highest frequency, 2 times 40K, so we're going to produce 80 kilohertz. So, and then determine the bit rate. The bit rate is equal to sampling rate multiplied with the number of bit per sample. So number of bit per sample is 4 multiplied with sampling rate. So we get 320 kilobit per second. So this is straightforward calculation. Okay. And then the bit rate of a pulse code modulation PCM is fixed at 63 kilobit per second. Calculate the bandwidth. Okay. So this is the question asks you to find the bandwidth PCM. It is not mentioned what kind of pulses used for the sampling process. So in this case, you can simply make it as bandwidth of PCM equal to the bit rate. Okay, this is the common equations for the bandwidth of PCM, which is equal to the bit rate. So this is therefore bandwidth of PCM equal to the bit rate. So we get 63 kilohertz. Okay, remember the unit must be in term of hertz. Okay, the unit for bandwidth is in term of hertz. Okay, the next example about bit rate and bandwidth of PCM. So this is one of the this is similar what we have asked previously in the previous final exam. Okay, we have asked these kind of questions actually. Okay, so this is also a good example for you to learn. Okay, so an analog signal with frequency of 4 kilohertz is sampled at sampling frequency 10% higher than the minimum Nyquist sampling frequency. That means we sample 10% more than the minimum Nyquist rate. So each sample is encoded with 3 bit PCM. So N is equal to 3 bit. Okay. Before it transmitted into the channel. Okay, we use a 3-bit system for the encoding process. Determine the bit rate. Okay, so in order to determine the bit rate, we need to know the sampling rate, then we can determine the bit rate. Okay, so the sampling rate. Okay, the sampling rate, first of all, we need to find the sampling rate. So sampling rate is 10% more than the minimum Nyquist rate. Okay, 10% more than the minimum Nyquist rate. So we need to know what is the minimum Nyquist rate. Minimum Nyquist sampling rate would be 2 times FM, 2 times 4 kilohertz. 4 kilohertz is the highest input frequency. So we get 8 kilohertz for the minimum Nyquist sampling rate. The minimum sampling rate would be 8 kilohertz. However, we sample at 10% more than the Nyquist rate. So that means 10% higher means that the minimum sampling rate plus 10% of minimum sampling rate. Okay, so 8 kilohertz plus 10% of minimum sampling rate, which is 10% of 8K, so we get 0.8 kilohertz. So total is 8.8 kilohertz. So actually, we sample at 8.8 kilohertz. Okay, 8.8 kilohertz is 10% higher than the minimum Nyquist rate. Okay, so after we know the sampling rate, then we can determine the bit rate. The bit rate is equal to number of bit per sample multiplied with the sampling rate. Okay, so 3 times 8.8 kilohertz, so we get 26.4 kilobit per second. Okay, so we just need to multiply the sampling rate with the number of bit. Okay, so if you see from here, the way we calculate the 10%, the way we calculate the 10% is minimum sampling rate plus 10% higher. Okay, that means 8 kilohertz plus 0.8 kilo. So we get 8.8. Okay, in the previous semesters, students tend to do careless mistakes about this. Okay, about how many percent more than the sampling rate. Okay, so they confuse about these calculations. Okay, remember that if 10% more or 20% more, we need to determine the minimum Nyquist rate first, then plus with the additional percent. Okay, so in this example is 10%, so we get 8.8 kilohertz. Then what about the bandwidth? The bandwidth of PCM. So you see that the question straightforward does not mention about what kind of pulses we used during the sampling. Okay, so in this case, you can just make the bandwidth as equal to the bit rate. Okay, simply put the bandwidth equal to the bit rate. So it is equal to 26.4 kilohertz. Remember, the unit is hertz. Okay, so the bandwidth of PCM is equal to the bit rate, but the unit is in terms of hertz. Okay. Okay, so the next process. Can I get your response? Can you hear my voice? Can you see my screen?
Yes, Doctor.
Okay. Okay, thank you for the response. Okay, thank you for the response. So the next process, the next topic is baseband transmission. Okay, baseband transmission. You see that now the issue is we already generate the PCM code word in the form of a digital code word 10101010 and so on. Okay, after encoding, we produce a digital code word. Now the issue is, how are we going to transmit this digital data into the medium? Okay, the issue is, how are we going to transmit this? Okay, one of the method is to use the baseband transmission. So the word baseband transmission, the word baseband here means that we are using the original frequency of the input signal. Okay, we are not going to translate the frequency into radio frequency. And this process does not involve modulation with the analog carrier. Okay, we simply use the original frequency of the input. Okay, it does not involve with the carrier in this process. We just use the encoding process. So for the baseband transmission, we are going to use the original input frequency signal. And normally we use a baseband transmission for the wired transmission. Okay, normally we transmit through the wired medium. So what we will do is, actually we will convert the digital code word into digital pulses. Okay, could you please mute your microphone, please mute your microphone. Okay, so now we want to convert the digital code word into digital pulses. Okay, how we want to convert that? We can use the line coding. So line coding is part of the channel coding. So there are many types of line coding. We have non-written to zero, written to zero, phase encoded, multi-level binary, and so on. Okay, and this is the example. This is the graphical representation of the digital pulses. Okay, so you see that picture A, we have the digital data. Now we want to convert it into digital pulses that consists of electrical voltage. Okay, voltage variation. So the picture B is a pulse representation of PCM. This is what we call as unipolar. Unipolar means that we only have single polarity. In this case is positive polarity of voltage. And picture C shows the bipolar pulses, which consists of positive polarity of voltage and negative polarity of voltage. Okay, so during the transmission, we have the options either to use a unipolar or bipolar transmission. Okay, bipolar pulses or unipolar pulses. Okay, so these are uh, the electrical pulses produced uh, using the line coding. Okay, so these are the pulses that we transmit through the medium. Okay, so you see that now our input is in the form of digital. Okay, because we have convert into digital code word. Okay, we have convert into digital code word, which is 1011001101. Okay, and the first line coding here is the non-written to zero. L is level. Okay, non-written to zero means that the waveform will not return to 0 volt. Okay, for example, here if you see that logic 1 input will produce positive voltage. Okay, logic 0 will produce negative voltage. Logic 1 positive, logic 1 positive output voltage, logic 0 negative voltage, logic 1 positive, negative, and positive. So this is non-written to zero level. Okay, then the second one is non-written to zero mark, M mark. Okay, so again, non-written to zero means it will not return to 0 volt. Okay, so the word mark here means that it will alternate whenever the input is logic 1. Okay, so you see that at the beginning, logic 1 produce positive voltage, logic 0 no change. Okay, no change, remains the same. Then we have logic input logic 1. Input logic 1 will alternate the previous polarity. So from positive becomes negative output voltage. Okay. Then another input logic 1, it will alternate from the previous values, which is negative voltage becomes positive. Then logic 0, no change. Another logic 0, no change, no change. Then logic 1, alternate from positive to become negative output voltage. Then positive, no change, then negative. Okay, this is for NRZ mark. And then NRZ space. NRZ space means that whenever the input is logic 0, it will alternate the polarity. And if the input is logic 1, no change. Okay, so this is inverse from NRZM actually. So for example, at the beginning, it doesn't matter whether it is positive or negative. So at the beginning, it doesn't matter whether it is positive or negative. So at the beginning, and then the next input is logic 0. Logic 0, it will alternate the previous voltage polarity, which is negative, to become positive. Input logic 1, no change. No change. Then input logic 0 will alternate the polarity from positive to negative. And then alternate again, no change, no change. Then input logic 0 will alternate the output, and then no change. So this is non-return to 0 space. So non-return to 0 is in the category of bipolar because we have positive and negative output voltage. Okay. Now, if we see the unipolar, means that single polarity, return to 0. That means the signal will always return to 0 volt at half of the bit time. Okay, so what is a bit time? Maybe I should explain here. The bit time is the bit duration for the duration for 1 bit. Okay, this is the bit time. So for RZ, within the bit time, the output voltage gonna always return to 0. Okay, so input logic 1 will produce positive output voltage at half of the bit time and then return to 0 volt. Input logic 0 will produce 0 voltage at the output. Okay, zero voltage at the output. And then input logic 1 produce positive output voltage half of the bit time and then return to 0. And then positive, return to 0. And then 3 input logic 0 produce 0 volt at the output. Okay, and then logic 1, return, positive, return, 0 volt, positive voltage, return to 0. This is unipolar, return to 0. Now we have bipolar, another one, bipolar, return to 0. That means input logic 1 will produce positive voltage and then return to 0. Input logic 0 will produce negative voltage and then return to 0. Okay, for example, here input logic 1 will produce positive output, return to 0. And then input logic 0 produce negative voltage and then return to 0. Input logic 1 positive, return to 0. Input logic 1 positive, return to 0. And then input logic 0 negative output voltage, return to 0. Then negative output voltage, return to 0. Negative output voltage, return to 0. Positive output voltage, return to 0, and so on. Okay, so this is bipolar, return to zero. Another one is return to zero alternate mark inversion, AMI. Okay, so here is return to zero means it will always return to 0 volt. Okay, but now it is alternate. So alternate here means that it will alternate the polarity whenever the input is logic 1. Okay, so for example here, initially doesn't matter. For example here, input logic 1 produce positive, output voltage return to 0. Input logic 0, no change at 0 volt. Okay, remains at 0 volt. Then input logic 1, okay, input logic 1, it will alternate from the previous. If the previous is positive output voltage, now becomes negative output voltage, then return to 0. Then another input logic 1, so it will alternate from negative to positive output voltage. Input logic 0, no change, remain at 0 volt. Then input logic 1, alternate from the previous input logic 1. So from positive to becomes negative. Output voltage return to 0. Then alternate again, positive, return to 0. Remains the same. Then input logic 1 again, then alternate to negative output voltage, return to 0. Okay, so this is uh, the RZ AMI. Okay, so the rest you can read on your own on the right side. The graph on the right side you can read on your own. So you see that these are the digital pulses that we use for the transmission. Okay, it is in the form of electrical pulses with positive voltage and negative voltage. So these are the things that we transmit. Okay, so these are the explanation for the waveforms. Okay, you can read on your own. Okay, you can read on your own. Then I move to the digital modulation. Okay, so now is about digital modulation. So in the previous topic, baseband transmission. So baseband transmission, we are using the line coding to produce the digital pulses. And normally for the baseband transmission, we transmit through the wired medium. Now, when we talk about digital modulations, we are actually transmitting as a bandpass transmission. Okay, so digital modulation here is under the category of bandpass transmission. So in this topic, we want to transmit the digital code word through the wireless medium. Okay, when we want to transmit the digital data through the wireless medium, that means we're going to convert into electromagnetic waves. So electromagnetic waves is analog. Okay, it's an analog signal. So now the issue is now we want to convert digital code word into analog signal for transmission through the wireless medium. We want to convert into RF signal, radio frequency signal. So this is also known as the digital radio transmission. Okay, for this topic, we are going to use analog carrier. We are going to do the modulation of analog carrier with the digital code word. Okay, with the digital code word. So now when we do the modulation with analog carrier, remember that there are three possible characteristics that will change during the modulation process. So if you remember that the characteristic of the carrier that will change during the modulation, first is amplitude of the carrier can change. Amplitude. Okay, the amplitude of the carrier can change during the modulation process. Then the frequency of the carrier. Okay, And then the last characteristic would be the phase of the carrier. So if during this process, so now we modulate digital code word with analog carrier. So during the modulation, if the amplitude of the carrier change in accordance with the digital code word variation, it will produce amplitude shift gain. Okay, and if the frequency of the carrier change during the modulation with the digital code word, it will produce frequency shift keying. And if the phase of the carrier change during the modulation process, it will produce PSK, phase shift keying. Okay, so these normally we transmit through the wireless medium. Okay, so these are the basic block diagram for the digital modulation techniques, okay, which consists of transmitter on the left side and also the receiver on the right side. Okay, so you have the input data, we have the precoder to encode the signal, and then we do the modulation in the modulator with analog carrier. Okay, so we have here is the analog carrier. We do the modulations, and then it's going to produce the upper sideband and also the lower sideband. We use a band pass filter, and then we amplify the signal. And then it transmits through the medium. The medium consists of noise. And then at the receiver side, we can use a band pass filter to select the desired frequency. Then we amplify the signal. Then we do the demodulation process. So during the demodulation process, we inject with the analog carrier again, the same carrier that we use during transmission. Okay, and then we produce the output data. So this is in the form of digital. Okay, so we have digital input. Okay, we have the digital code word input. We produce digital data at the output. Okay, and this is the energy bit over noise density. Okay, so EB over N0. So EB over N0 is the performance parameter in digital system, which equivalent to the SNR in the analog. So normally in the digital, we use the EB over N0 compared to the SNR. Okay, so these are very important parameters to determine the quality of the received signal. So EB is the average bit energy, N0 is the thermal noise power density. Okay, the equation for energy bit is equal to received power multiply with bit duration. Okay, so watt second, which is in terms of joules, and then N0 is equal to Boltzmann constant multiplied with the noise temperature at the receiver side in terms of Kelvin. Okay, so EB over N0 is actually measured at the receiver side. Okay, these are the parameters measured at the receiver side. So in your syllabus, we are in this chapter 4, we are not playing around with the EB over N0. Not much we will learn about these parameters. So you're going to see these parameters a lot in digital communication subject, in another subject. But in this chapter, we're going to learn briefly about EB over N0, the energy bit over noise power density. So the next parameter is channel capacity. So what is channel capacity? Channel capacity is the highest possible bit rate. Okay, channel capacity is the highest possible bit rate that can be decoded at the receiver side. Okay, so C for capacity is equal to 2 times bandwidth log base 2 of M. Okay, M is the number of unique symbols. Okay, so the minimum bandwidth necessary to pass the MRI, digitally modulated carrier, which is the minimum Nyquist bandwidth in Hertz, is equal to the bandwidth divided with log base 2 of M. Okay, so this is the minimum bandwidth. Okay, the minimum bandwidth needs to pass the Emery transmission. What is Emery actually? So Emery is the way we it is referring to the number of symbols for each of the modulation techniques. Okay, so you remember that previously I've mentioned about ASK, FSK, and also PSK. All of these consists of um, many variations. So actually, there are the way we in theoretically actually we can write like this: M dash ASK, M dash FSK, or M dash PSK. So within each of these modulations, there are a few sets of variations within this category. Okay, where M is the number of symbol. M is equal to, okay, M is equal to 2 power of N number of bit. Okay, for example, I'm using 2-bit, that means 2 power of 4. Okay, sorry, 2 power of, I'm using 2 bits, so that means for example, sorry, if I'm using 2 bits, that means I'm gonna have M equal to 4. So 4 here means that I'm gonna have 4 unique symbols, okay, which is 0, 0, 0, 1, 1, 0, and 1, 1. Okay, and if I'm using ASK, so if I'm using ASK, I do a ASK modulation. So the way I can write is ASK. So this is just example. If I'm using a 2-bit FSK, that means I can write is 4 dash FSK. If I'm using PSK modulation with 2-bit, so this is 4 PSK. Okay, so M is 2 power of N. Okay, and if you see from here, this one, M is actually 2 power of N. So this is K is the number of bit. So don't be confused. In this slide, this is actually equivalent, same as N number of bit. So the different here is using K. So K, if you see that some literature books use K instead of N. Okay, K and N are the same thing, which is the number of bit. Okay, so K is N, K or N is equal to log base 2 of M, or M equal to 2 power of N. Okay, the same thing. So therefore, bandwidth is equal to the capacity divided with K number of bit. Okay, so this is how we calculate the, so this is actually similar with this one. So if we consider the maximum bit rate, that means it is a capacity. Okay, capacity is the maximum bit rate. So don't be confused about that. The interchange of capacity and B. Bit rate is the normal bit rate. Okay, the speed of transmission. But when we talk about capacity, channel capacity, this is referring to the maximum bit rate that can be transmitted and decoded by the receiver. If we transmit more than the channel capacity, what happened? The receiver will be unable to decode the received signal. That's the issue, okay? So the transmitter needs to know what is the capacity, channel capacity. The transmitter should not transmit more than the channel capacity. Otherwise, the receiver will be unable to decode the received signal. Okay. So another parameter is the baud. Baud is a symbol rate. Okay. Baud is a symbol rate. So the maximum baud. Okay. So when we talk about maximum baud, which is the capacity divide with the number of bit. Okay, divide with the number of bit. So this is actually bit per second. divide with number of bit. So you divide with number of bit per number of bit per symbol. Number of bit per symbol. Okay, so this is bit per symbol. Bit per second divide with bit per symbol. So what you will produce is actually symbol per second. Okay, so bit per second divide with symbol, divide with bit per symbol. Okay, so maybe I can do like this, and bit per second. You divide with bit per symbol. Okay, so actually bit and bit you can cancel out, so it is become symbol per second. Okay, what you will produce is a value symbol per second. Okay, what is symbol? Okay, so in my example, if I'm using 2-bit, okay, if I'm using 2-bit, so each of these is a symbol. Okay, 0 0 in my example, if I'm using 2-bit, so each of these combination is each of these 2 bits are called as a symbol. Okay, the first symbol, okay, the second symbol, third symbol, and the fourth symbol. Okay, so symbol rate or the baud rate determine how many symbol I can send in 1 second. Okay, different from bit rate. Bit rate determine the number of bit you can send in 1 second. But for symbol, it determines how many symbol you can send in 1 second. Okay, so the symbol rate is in terms of symbol per second, or what we call as baud. Okay, simply as baud, or we can say that it is symbol per second. Okay, so the first type of digital radio transmission is ASK. So ASK is when we do modulation of digital code word with analog carrier. Okay, so we still use the same, almost the same parameters that we learn in chapter 3 actually. So for example, here the carrier is equal to VC cos omega CT plus theta. So the general equation for ASK is this one, 1 plus VMT. VMT is VM cos omega MT, multiplied with VC cos omega CT. So this is the general equation for ASK. So now what we want to see is that this parameter will change, the VMT. So the VMT in digital is either logic 0, or logic 1. Okay, so there are only two possibilities, either logic 0 or logic 1. Okay, so in digital, we are not using VMT equal to VM sine 2 pi FMT, not like that. VMT is either logic 0 or logic 1. Only two possibilities. Okay, so you see that if the input is logic 1, okay, if the input is logic 1, that means VMT is equal to 1. So 1 plus 1 multiplied with a carrier, so we're going to produce 2 VC cos omega CT. Okay, and if the input is logic 0, okay, the input is logic 0, that means VMT will produce negative voltage. Okay, VMT becomes negative voltage. So this is we consider as a bipolar input. So negative, so logic 0 is representing as negative 1 volt. So we put inside the general equation, it becomes 1 minus 1 cos VC cos omega CT, which is equal to 0. Okay, so only two possibilities, either this or this. Okay, either logic 1 or logic 0. Okay, so you see that if logic 1, that means if the input is logic 1, we have output signal. If the input is logic 0, no output signal. Okay, as if it is switched off, as if. Okay, so you see that, for example, like this, for the input 1 0 1 0. Okay, input logic 1 0 1 0. So the output is 2 cos omega 2 VC cos omega CT. Okay, and then 0, and then 2 VC cos omega CT, and then 0. So this is like switch on, switch off, switch on, switch off. Okay, that's why another name for the ASK is on off keying, OOK. Okay, another name for the ASK is OOK. And this is the waveform and also the spectrum for the ASK. So if you see from here, for the waveform, okay, we have input logic 1 0 1 0 1 0 for the VMT. The output VASKT is 2 VC cos omega CT, and then logic and then 0 output, and then 2 VC cos omega CT, and then 0 output, has signal, 0 output. Okay, so this is on off keying. What about the spectrum? Okay, so the spectrum, for example, here we have for the VMT, the input consists of FM, 3 FM, 5 FM. So we have a 3 input here. Okay, so what about the bandwidth? So if we consider up to 5th harmonics, okay, that means the bandwidth is 2 times 5 FM. Okay, the way we calculate the bandwidth is actually 2 times FM, but in this case we have up to 5th harmonics. That means the bandwidth is 2 times 5 FM. Okay, so depending on the how many inputs do we have, is it up to 5th harmonic, 10 harmonic, 20 harmonics, and so on. Okay, so we just need to multiply it with 2. Okay, 2 times the input. Okay, 2 times the input. And if you see from here, OOK can be done using multiplier circuit. So this is the modulator circuit, using a multiplier circuit in transmitter to produce the ASK. So for example, here we have the input is 10110001. So we multiplied with the analog carrier over here. So here we have the multiplier circuit. So what happened is that it will multiply in mathematics. Okay. So what happened here is input logic 1, we have output voltage 2 VC cos omega CT, and then input logic 0, 0 output. Okay. Input logic 1, switch on, another input logic 1, switch on, and then off, off again, and then we have output for the input logic 1. Okay, so this is at the receiver side. And what happened at the receiver side when we want to do the detection process or demodulation process? So for the coherent detection means that we have the carrier as the external signal that we inject to the demodulator circuit. Okay, so for the coherent means that we use carrier information to do the demodulation process at the receiver. So whenever we have the carrier component here, it is under the category of coherent. That means we use the carrier information for the demodulation process. So now this is at the receiver side. We receive OOK signal. We multiplied with the carrier information or carrier signal with frequency FC. So we're going to produce a upper sideband and also the lower sideband. So the LSB and also the USB. So we want to have the lower frequency signal at the output. So we use a low pass filter to select the low frequency signal and remove the higher frequency. And these are the parameter. These are the important parameter, what we call as a bit error probability. Okay, the probability that the bit received at the receiver is in error. Okay, this is the probability calculations, which is this is for the coherent detection. So this is the probability of bit error that we measure at the receiver side. Okay, what is the probability that the bit gonna be error? Okay, at the receiver. Okay, ini adalah kebarangkalian berlakunya error at the receiver. So it is for ASK with coherent detections, it is 1/2 complementary error function. I suggest you to put bracket square root of EB/2N0. This is energy bit over noise power spectral density. Okay, and ERFC is the short term for complementary error function. Okay, for example, here ERFC of Z is equal to 1 minus error function. ERF is the error function of Z, where ERF is the short term for error function. So you see that there are two tables here. The first one is the error function table. The second table is the complementary error function. Okay, so how to read this table? For the first table, okay, perhatikan class. For the first table, for example, here the input X is 0.4. So therefore, you see that this table consists of X values from 0.0 until 3.2, and another decimal point from 0 until 9. Okay. So for example, if the input is 0.40, if X is equal to 0.40, the output is gonna be it's gonna produce 0.42. The output gonna be 0.428423839. Okay, the output gonna be 0.42839. Okay, the error function at the output gonna be 0.42839. And for example, if X equal to 0.45, okay, 0.45, okay, the ERF of 0.45 is equal to 0.475 548, and so on. And for example, if the input is 2.43, for example, okay, if X is equal to 2.43, therefore the error function ERF 2.43 is equal to 0.999, 0.99941, and so on. So this is how we read the table. For the second table is also similar. Okay, for example, here is 0 if X equal to 0.40. So for the complementary error function ERFC function 0.40, this is equal to 0.57161. And another example, if X equal to 0.45, for example, therefore the complementary error function ERFC of 0.45, this is equal to 0.5245252. Okay, so this is how we read the table. Okay, X, we know the X, and then we can find the answer of complementary error function. So let's do the example so that you know how to do this. Okay, Actually, these are among the favorite question that we asked in the previous final exam. Okay, later in the exam, you will be given the table. Okay, you will be given the ERFC table, and if there is a question about this, you will be given EB over N0, for example. Find the probability of bit error using, if we are using the coherent detection at the receiver. Okay, given EB over N0 is 0.32. How much is the probability of bit error? Which is equal to 1 over 2 complementary error function of square root of EB over 2N0. So we rearrange the equations. We put outside the 1 over 2, and then this is EB over N0. Remember, this is in the ERFC function. Okay, so square root of 1 over 2 EB over N0. So that means we can rewrite like this. Okay, 1 over 2 complementary error function, square root of 1 over 2, 0.32. 0.32 is given in the question, which is this one. Okay, so you solve the parameters inside the bracket first. Okay, which is square root of 0.16. Okay, which is this one, square root of 0.16. Therefore, we get 1 over 2 complementary error function of 0.4. Okay, so we can refer to the complementary error function table for x 0.40. Okay, x 0.40, which is this one. We're going to produce complementary error function with equal to 0.57161. Okay, so we can put this value inside the equations. Okay, so this one, ERFC of 0.4 produce 0.57161. So this is we get from the table. Okay, if you want to use the ERF table, you can also do like this. If you are using the first table, 1 minus ERF. Okay, ERF 0.4. So if you see from the first table, okay, the first table ERF table, which is this one, you're going to produce 0.42839. This is if you use the first table. Okay, if you use second table, you can find this answer. So which one should we use, the first or second table? I would suggest you to use the second table, which is straightforward. Okay, if you use second table, you can directly get the answer, which is ERFC 0.4, you get 0.57161. Okay, if you want to use the first table, you need to minus with 1, which is take another time. Okay, so imagine, for example, we use the second table, the complementary error function table. We get the ERFC 0.4. We put inside the values. We put inside the values, which is now we already get ERFC 0.4. It is 0.57161. Remember to multiply it with 1 over 2, half. So we get the probability of bit error at the receiver side. So that means if the EB over N0 is 0.32, the probability of bit error at the receiver using a coherent detection would be 0.2858. Okay. These are the probability that the error gonna happen at the receiver side. Okay, this is an important parameter that we use to know how much is the probability of the bit error. So this is also ASK, probability of bit error, but now we are using non-coherent. So what if we are using non-coherent detection at the receiver? Okay, so if you're using non-coherent, that means the equation would be 1 over 2 exponent power of minus EB over 2N0. Okay, so for this non-coherent detection, the probability of bit error can be calculated directly using the calculator. So in this case, you don't need to use the table anymore. Okay, for example, given EB over N0 1.11, for example, okay, using a non-coherent detection, find the probability of bit error. So you can write 1 over 2 exponent minus EB over 2N0. Okay, so this is, if you rearrange the equation, we can put outside the 1 over 2. Okay, so we know the EB over N0 1.11. So put inside the equations, minus 1.2, minus 1 over 2 multiplied with 1.11. So try use your calculator now. Okay, try use your calculator. Okay, so if I'm using the normal calculator, I should press shift ln. Shift ln is exponent, for example, in my calculator. So for example, before I use exponent, I need to solve the parameter above 1.11 multiplied with minus 1 over 2. So it is minus 0.555. Okay, so exponent power of minus 0.55, how much? So shift ln negative 0.555. So I get 0.5741. Using calculator, I can get this value 0.5741. If I'm using my calculator, I'm gonna press shift ln. Okay, press shift ln, you're gonna get exponent power of how much? So you're gonna get the probability of bit error is 0.2870. Okay. So class, if you have question, please ask me. Please interrupt my lecture. You are most welcome to ask question. Okay. So in the previous final exam, we have asked this kind of question, where we give the value of EB over N0, and the student needs to find the probability of bit error. Okay, so let's look another type of modulation, which is the FSK. So FSK is the modulation type that change the frequency characteristic of the carrier. Okay, so given the general equation for FSK is VC cos big bracket 2 pi FC plus VMT delta F, close big bracket here. Okay, so the thing that we're going to change is actually the VMT. The VMT will change. So VMT has two possibilities, either logic 0 or logic 1. Okay, if VMT is logic 1, that means it will be represented with 1 volt. Okay, if VMT is logic 0, it will be represented as minus 1 volt. Okay, so you see that what happened here is actually if the input is logic 1, so therefore the equation is VC cos 2 pi FC plus. So this is actually plus delta F. So no need to write VMT here. So FC, this is a FC plus delta F. Okay. And if the input is logic 0, VMT will be represented as minus 1. Okay, minus 1. So therefore, the output gonna be, this one is actually FC minus delta F. Okay, so it is either FC plus delta F or FC minus delta F. Okay, so this is for input logic 1, the output is a high frequency. For input logic 0, the output gonna be low frequency. Okay, and the bandwidth for this FSK is measured as 2 times delta F plus B. Okay, B here is the input frequency. B here is the input frequency, which is FM, F of the message. Okay. So how we want to generate the FSK signal? So we can use this kind of modulator. For example, here you see that we have two oscillator, two modulator circuit. Okay, two balance modulator. The first balance modulator and the second balance modulator, and we have two oscillator frequency. F1 is higher than the frequency of the second oscillator in this example. Okay, so for example, here we have an input 1 0 1 0. Okay, so this goes through the first balance modulator, which will be multiplied with frequency signal of F1. So what happened here is when we multiplied analog signal with a digital input. So here you see that for the input logic 1, we have a signal, input logic 0, 0 output, input logic 1 has a signal output, and then 0 output. So this is like a ASK signal. Okay, and then the next the input also will go pass through the inverter. Inverter mean it will inverse. So it will inverse logic 1 with logic 0, logic 0 with logic 1. So the input gonna be inverse. For example, here 1 0 1 will be changed to 0 1 0. Okay, so 0 1 0 will be passed through the second balance modulator, multiplied with the oscillator, second oscillator with frequency F2. F2 is smaller than F2 is smaller than F1. Okay, the frequency is lower than F1. So you see that for logic 0, no output, switch off. Logic 1, it has a output signal, but low frequency. Okay, and then logic 0, no output. Okay, so this second signal plus with the first signal, the first signal plus the second signal, it will produce an output like this. Okay, high frequency, low frequency, high frequency, and so on. So this is for logic 1, logic 0, logic 1. Okay, similar with the picture below using frequency modulated oscillator. Okay, and if you see the waveform of the FSK is like this. So imagine that we have the binary input 0, logic 0, logic 1, logic 0, logic 1, and so on. Remember, logic 0 will produce low frequency output, which is what we call as the space frequency, Fs. Okay, space frequency to represent logic 0, or this is a low frequency. For input logic 1, it will produce high frequency at the output. So the high frequency, we allocate the terms is FM. FM is for the mark frequency. Mark frequency is high frequency, which is assigned to input logic 1. So you see that if the input is like this, 0 1 0 1 0 1, so the output gonna be low frequency, high frequency, low frequency, high frequency, and so on. Okay. So input logic 0 produce low frequency, input logic 1 produce high frequency at the output. Okay. And this is the waveform of FSK based on the logic input 1 0 1 0 1 0. So you see that high frequency, low frequency, high frequency, low frequency, high frequency, low frequency. Okay, as I mentioned before in the class that if the ripple is close one another, it is a high frequency. If the ripple is further away from one another, it is a low frequency. Okay, so from the ripple, we know that which one is high, which one is low. Okay, daripada gelombang itu kalau kita lihat dia rapat-rapat, maknanya dia adalah high frequency. If the gelombang is jarak-jarak, that means it is a low frequency. So if you see the way we calculate the bandwidth is based on the Carson's bandwidth, which is 2 times Fm plus delta F. Okay, 2 times Fm plus delta F. So in this example, it is up to the fifth harmonic. That means the bandwidth for the fifth harmonic is 2 times 5 Fm plus delta F. So this is using the Carson's method to calculate the bandwidth. Okay, so it is a estimated bandwidth. And the way we want to generate the FSK, okay, so sorry, this is at the receiver side. At the receiver side, the way we want to do the demodulation, the first one is the coherent detection. Coherent detection means that we have the carrier information which we supplied to the multiplier. So for coherent detection, we need to use the same carrier information that we transmit at the transmitter. Okay, we are using the same carrier from the transmitter, the same carrier frequency. Okay, so whenever there is a carrier information used in the system, it is a coherent. Okay, so here, for example, we have a FSK input and then put inside the power splitter to split the power difference. And then we separate the difference of power, one to go to the first multiplier and the other one is for the second multiplier. Okay, then the multiplier will do the multiplication process mathematically, which will produce a lower sideband and the upper sideband. Okay, it consists of lower sideband LSB and also the USB. So similar with this one, LSB and USB. So we want the low frequency signal, so we use a low pass filter, and then we can produce the output in terms of logic 1 and also logic 0. And the picture below, picture B, is for the non-coherent detection, where we don't use the carrier information at the receiver side to do the demodulation process. So imagine if you have a FSK input, we split the power difference. One goes to the first band pass filter, another one goes through the second band pass filter. So the first band pass filter is centered at space frequency. The second band pass filter is centered at Mach frequency. That means we want to capture space frequency and the Mach frequency. Okay, and then pass through the envelope detector. Envelope detector is similar with the AM detector. Okay, which will do the demodulation like in the AM process, and then produce the output in terms of logic 1, logic 0, logic 1, and so on. So this is for the FSK. And if you see from here, the probability of bit error for the FSK is similar with the probability of bit error for the ASK. Okay, FSK and ASK, the way we calculate the probability of bit error is the same. Okay, for coherent and also for the non-coherent, the equation is the same. And if we look to the third type of modulation, which is phase shift keying, okay, the last type, which is a PSK phase shift keying. So for phase shift keying, if the phase of the carrier change during the modulation process, it will produce PSK. Okay, and remember that I mentioned that the way we can write the modulation for PSK is Emery M PSK. Okay, for M PSK, that means M can be determined based on the number of symbols. So if I use a binary 1 bit, Okay, that means m equal to 2 power of 1, which is 2. Okay, that means I only have two possibilities, either logic 0 or logic 1. Okay, so if I'm using the 1 bit only, okay, if I'm using 1 bit only, it is called as BPSK, binary phase shift keying. Okay, I'm using 1 bit and I have two possibilities of output, either logic 0 or logic 1. Okay, so if I'm using BPSK, the difference between logic 0 and logic 1, it is separated by 180 degrees phase shift. Okay, because we are talking about PSK, so each bit will shift the phase of the carrier. So in this case, if it is a BPSK, so logic 0 and logic 1 is separated by 180 degrees. Okay, so we're going to see later about this 180 degrees later, okay, after this. And this is the generation of a BPSK signal. So this also we have asked in the previous final exam a long time ago. We have asked this question. The same picture we use in the final exam, where the student needs to determine the signal. Okay, so for example, here we have the binary data, unipolar. Okay, this is a unipolar, and then goes through the level converter to convert unipolar into bipolar. Okay, which consists of two polarity, positive and negative, and then put inside the balance modulator. Balance modulator, remember, balance modulator will multiply with another signal, which is sine omega CT. So whenever you multiply two input, okay, you're going to produce upper and lower sideband, okay, and then we're going to need a filter to select the desired frequency, and then we transmit. Okay, so what happened here is actually, so we have only two possibilities, either positive, okay, either positive or negative input. Okay, so positive one or negative one, for example. So the output here is either negative sine omega CT or positive sine omega CT. Okay, so if the input is logic 0, we're gonna produce negative sine. If the input is logic 1, we're gonna produce positive sine omega CT. So how does it looks like for positive and negative actually? So for positive sine, it is like this. Okay, so this is sine omega CT. What about negative sine? Negative sine is gonna be inverse. That means it's gonna be like this. Okay, so this is negative sine omega CT. Okay, so either this one we're going to transmit. Okay, either we want to transmit negative sine omega CT for input logic 0, or positive sine omega CT for input logic 1. Okay, and at the receiver side, okay, at the receiver side, the input is, okay, now we talk about at the receiver side. So at the receiver side, either we receive a positive sign or negative signs. Okay, so either if it is a logic 0, we're gonna receive negative sign omega CT. If the bit that transmitted is logic 1, we're gonna receive positive sign omega CT at the receiver side. Okay, go pass through the band pass filter, And then since this is a coherent detections, so at the balance modulator, we multiplied with another sine function. Okay, so sine multiplied with sine. Okay, we're gonna produce a lower sideband or upper sideband. Okay, so since we want to get the low frequency signal, so we use a low pass filter to get the LSB, and then level converter to convert from bipolar to unipolar. So we produce unipolar output. And these are the equations at the receiver side. Okay, so these are the things that we asked previously in the previous final exam a few semesters ago. Okay, so what is the output of the balance modulator? So imagine if we receive a positive sine omega ct. This is actually, we know that it is the transmitter transmit logic 1 actually. So the output of the balance modulator, okay, the output of balance modulator is sine multiplied with sine. Okay, so sine, okay, from the input multiplied with the oscillator, okay, multiplied with the carrier oscillator. So you're going to produce sine square. So sine square according to Trigo is 1/2 1 minus cos 2 omega ct. So you see that this one, so sine square, you see that we have a 1/2 a DC voltage minus a 1/2 cos omega ct. So this is a high frequency. This is a high frequency. So high frequency, when we pass through the low pass filter, it will be filtered out after the low pass filter. So after low pass filter, it will leave the positive 1/2 or logic 1 because it is a positive. So this is after the low pass filter. And if the band pass, if the BPSK receiver receive negative sine omega ct, okay, imagine if we receive a negative sine omega ct, what happened? Okay, so negative sine omega ct is actually representing by logic 0. Okay, that means we know that the transmitter actually transmit logic 0 actually. So that's why we receive negative sign. Okay, so input to the receiver negative sign multiplied with the local oscillator sine omega ct. So we get negative sine square. And according to Trigo identity, negative sine square is equal to negative 1/2 1 minus cos 2 omega ct. This is the signal that we're going to produce right after the balance modulator. You see that we have a high frequency component 2 omega ct. Okay, so we want to remove the high frequency component using the low pass filter. So we have the low pass filter over here to remove the high frequency component. Okay, so this component, the high frequency component, will be removed by the low pass filter, leaving minus 1/2. So 1/2 minus 1/2, since this is a negative polarity, so this is actually represented as logic 0 at the output. Okay, so this how the BPSK translate the input, the analog input to become logic output in digital. Okay, and this is the truth table, phasor diagram, and also the constellation diagram. Okay, this is very important in the digital transmission. So you see that for the truth table, we have two possibility: logic 0 or logic 1. So logic 0 is represented by output phase of 180 degree. Logic 1 is represented by 0 degree at the output. So you see that the difference is 180 degree. of logic 1 and logic 0. And if we draw the phasor diagram is the arrow diagram, is the arrow diagram. So you see that the arrow diagram, the way we want to draw is, you see that the y-axis is for the cosine parameter, for the positive cos and negative cos below. Okay, this is a y-axis, and for the x-axis is from minus sine omega ct until positive sine omega ct. So this is the cos versus sine diagram. So for the phasor diagram, or we can say that the arrow diagram, how we're going to draw is that for logic 0, it is pointed to 180 degree. And for logic 1, it is pointed to 0 degree. Okay, so this is a quadrant diagram also. You see that from 0 degree, 90 degree, 180 degree, 270 degree, and then so we get 360 degree. Okay, so we have the first quadrant, second quadrant, third quadrant, and also the fourth quadrant. Okay, so the arrow diagram shows point to 180 degree and also point to 0 degree. So this is phasor diagram or the arrow diagram. Another one is the constellation diagram. Okay, the dot diagram. So we have two dots. One dot to represent symbol. Remember, we have two symbols. So the first symbol for logic 0 is located at 180 degree, and logic another symbol is logic 1 is located at 0 degree. So this is the dot diagram. Okay, so you see that it's quite strange to have two dots. Okay, later you're going to see that if the value of m is higher, that means we're going to have many dots over here. Okay, many dots. So what's the important thing of this? So the constellation diagram is to see the arrangement of the symbols. If the symbol is close one another, the probability of bit error gonna be higher. Okay, but we need more symbols so that we can transmit at high data rate. Okay, so you're gonna see this. You're gonna see at higher symbol after this. What if we have higher symbol? Okay, remember normally for the m, the maximum for m normally is 256. Okay, normally for the highest value of m is 256. So you see that for the BPSK, so now it's 10:30. Sorry, class. Maybe I need to take another half an hour of your time. Sorry about that. Just to finish a few more slides after this. Okay. Sorry about that. Before that, can I get your response? Are you still there? Can you see my screen?
Yes, Doctor.
Okay. Thank you for the response.
Yes, yeah.
Okay. Sorry, saya akan ambil masa sikit lagi. So here is the BPSK waveform. So we have the input logic 1, input logic 0, 1, 0, 1, 0. Remember, for input logic 1, we will produce positive sign. Input logic 0 will produce negative sign. Okay, negative sign start from negative. Input logic 1, positive sign. Input logic 0, negative sign. Positive sign, negative sign. Okay, so you see that this part is phase shift, 180 degree phase shift. Okay, and this is the waveform of BPSK and the spectrum of BPSK. So the way we calculate the bandwidth for the PSK is similar with the way we calculate the bandwidth for ASK, which is 2 times the fundamental input frequency. Okay, so if the input is up to 5th harmonics, that means 2 times 5 FM. Okay, and if you see that for the probability of bit error, okay, for the probability of bit error for the PSK, only PSK is different compared to the FSK and ASK. So what's the difference? Okay, what's the difference? You see that the difference is over here. There's no, previously is 1/2 EB over N0. So now is only EB over N0. So there's no 1/2. Okay, there's no 1/2 over here. Okay, this is for the coherent detection. And for the non-coherent, also different. So what's the difference? The difference is you see that there's no 1/2 over here. So previously is negative 1/2 EB over N0. Now for PSK, okay, only EB over N0. Okay, there's no 1/2. Okay, tidak ada setengah di sini. So only PSK different from ASK and FSK, the way we calculate the probability of bit error. Okay. Okay, maybe the last topic before we finish about the QAM. So QAM is the combination of ASK, okay, the combination of ASK and PSK combined. Okay, so these are among the, this is one of the high-level modulation techniques, okay, that has that are nowadays widely used even for the 5th generation of cellular communication system. Okay, for the for high-level modulation techniques, we normally use the QAM techniques. Okay, so here there's an example of 8 QAM. Okay, so what is 8 QAM? 8 QAM means that we are using 2 power of 3. So M is equal to 2 power of 3. So we're gonna get 8 unique symbol from 0, 0, 0 until 1, 1, 1. For 16 QAM, we're gonna use 4 bit. That means we're gonna have 16 unique symbol. Okay, so these are the block diagram for the QAM transmitter. Okay, so where we have the quadrature channel, in-phase channel, and control channel. Okay, remember we use a 3-bit. That means we have the Q bit, I bit, and C bit. Okay, Q is a quadrature, I for in-phase, C is a control channel. Okay, so for Q bit will go through the Q channel, I bit will go through the I channel. Okay, so I channel and Q channel will go through the 2 to 4 level converter. Okay, it will go through the 2 to 4 level converter. What is this actually? So you see that for each of the level converter, the control bit also will go through the level converter. That means the input to the level converter is 2 bit. Okay, level converter will receive 2 input bit. Okay, each level converter will receive 2 input bit, and it will produce 4 different output voltage. Okay, that means 2 input bit produce 4 unique output voltage, which is what we call as the PAM signal, pulse amplitude modulation signal. Okay, remember we have 2 input, that means we're going to have 4 possibility of output. If the input is 0, 0, 0, 1, 1, 0, and 1, 1. Okay, it will produce 4 different levels of output voltage, which is defined here in the table. Okay, so the table here is defined for this specific level converter. For example, if the input is logic 0, and 0 produce negative 0.541 volt. Input logic 0, 1 produce negative 1.307. Input 1, 0 produce positive 0.541. Input 1, 1 produce 1.307. So these are the table for the level converter. Okay, so now we produce voltage at the output. The output is based, there are 4 possibilities of voltage at the output. Okay, and then go pass through the product modulator. So product modulator will multiply with analog carrier. Okay, we multiplied with analog carrier. So you see that here, reference oscillator produce a sine omega ct, goes through the first product modulator. Then we have phase shifter, 90-degree shift of sine produce cosine. Okay, so the output here is x multiplied with sine omega ct. Okay, sine omega ct, and over here is y cos omega ct. Okay, and then put through the linear summer, we plus both of it, sine and cos, and then we have go pass through the band pass filter and then produce the output. Okay, so how do we determine the output, which is this one? Okay, so we have asked this previously. We have asked this previously in the quiz a few semesters ago. So let me explain to you about this, about the table, about the process happen at the transmitter. So the truth table for I and Q channel. So you see that okay. So can I get your response whether you can read whether you can read this slide or not? Is it possible to read the slide? Boleh nampak Okay, possible. Dia bila saya zoom saya tak boleh nak tulis kejap. So saya kena normal lah. So okay. So you see that we have the table for the level converter. So this is example. This is example for the QAM modulator. So you see that here for the first one, for the first example, imagine if we have the input 0, 0, 0. Imagine if you have the input 0, 0, 0, which is here 0, 0, 0. Okay, so what happened? So I channel will go here 0, and then the control bit is 0, and then Q channel 0, control bit 0. So what happened to the output of the level converter? Okay, so you see that here for I modulator, I product modulator, okay, it will produce negative 0.541. So you see that 0 and 0. 0, 0, if you refer to the table, it will produce negative 0.541. For the I channel, we will multiply it with sine function. Remember this one? We will multiply the first product modulator, we multiplied with sine omega ct. Okay, so negative 541 multiplied with sine omega ct, so we produce negative 0.541 sine omega ct. For the Q channel, okay, so for the Q channel, we multiplied the output. If you see that 0 and 0 produce 0 minus 0.541 multiplied with cosine. Q channel multiplied with cosine. So what is cosine? Kalau kita lihat cosine is this one. We multiplied with cosine for the second product modulator. We multiplied with cos. Okay, so we get negative 0.541 cos omega ct. and then goes through the linear summer. The linear summer will sum both of it, sine and cos. So you see that if you sum both of these, it is located at the third quadrant. Remember, this is a cos, this is negative cos diagram. This is a sine, this is a negative sine diagram. So if it is a negative cos and negative sine, so it is actually located somewhere here. Okay, negative cos and negative sine. Okay, it is located somewhere here in the third quadrant. First, second, third, fourth quadrant. So it is actually located at the third quadrant. So how do we determine what is the value at the third quadrant? Okay, so the way we want to know the magnitude is summation of quadratic and then square root. Summation of quadratic, the magnitude 0.541 square plus 0.541 square, and then square root, and then you're gonna get 0.765 volt. Okay, and then what is the phase is arctangent negative 0.541 divided with 0.541, so we get 45 degrees. Arctangent is inverse tangent. Arctangent is inverse tangent. Okay, and we get 45 degrees. So remember, this is 45 degrees from here, 45 degrees from here, which is, this is 45 degree over here. So if you want to calculate from here, that means it is 90 plus 45. So it is actually minus 135 actually, minus 135 if we measure from x-axis. So that's why it is a minus 135. Okay, and if you see that, now we can rearrange the equation, so it becomes a 0.765 from the magnitude sine omega ct minus 135. Okay, so we write a single equations. 0.76. 0.76 means that the amplitude here is 0.765. Okay, wait. Is there any? Okay, so the amplitude here is, you see that this is the first. So if you see from the phasor diagram, it will be over here, 0, 0, 0. Okay, and back to the second input. So there are three possible input in this example. So you see that for the input bit, the next example, class, 0, 0, 0, 1 input. Okay, I would be 0, Q also 0, control bit is 1. So 0, 1, if you see from the truth table, you're going to produce negative 1.307. Okay, I channel produce negative 1.307. Q channel also produce negative 1.307, but cosine. After the linear summer, it will sum the cos and sine. So you see that negative cos and negative sine also located at the third quadrant. Okay, somewhere in the third quadrant. So how do we determine the magnitude? It is the summation of quadratic and then square root. So we get 1.848 volt. What about the theta? Okay, the theta. The theta is arctangent, shift tangent, minus 1.307 divided with 1.307, and then you shift tangent, you get 45 degree. Remember, when you want to use a calculator in this example, that means you need to use a degree mode. Okay, your calculator must be in degree mode. So you get 45, but 45 is actually over here, 45. So it is actually minus 90 minus another 45, so you get minus 135. So the output of the linear summer is actually 1.845 sine omega ct minus 135 degree. So if you draw the the phasor diagram, it is here, okay, for input 0, 0, 1. Okay, let's look for the third input. Okay, another, it's just for a few input. Okay, only 2 input and then we can finish. Sorry, I take your time. Another half an hour. So for the third example, class, please see this, that the input now is 0, 1, 0. Okay, 0, 1, 0 I channel will produce positive 541 sine omega ct. So if we see the truth table, it is actually this one, the third row, 1, 0, which is produce the positive 541, and then for the Q channel, it produced negative 0.541, which is the first row. Okay, the first row, 0 and 0. Okay, 0 and 0, and also 1 and 0. So I channel positive 0.541. Q channel produce minus 0.541. So multiplied with cos, so we get these two values, positive and negative. And then after the linear summer, so it's gonna plus a sine and cos. So you see that this is a positive sine and negative cos. Okay, so positive sine, okay, this is sine and negative sine. So positive sine and negative cos. Okay, positive sine, negative cos. So it is somewhere at the fourth quadrant. So first, second, third, fourth quadrant. Dia terletak pada fourth quadrant. But how much is the magnitude? The magnitude is quadratic summation and then square root. So we get 0.765 volt. What is the degree? So the degree here is, how much is this? Theta. So the theta is arctangent 0.541 divide with negative 0.541. So we get negative 45 degrees. So the way we calculate, we simplify the equations to become 0.765 sine omega ct minus 45 degrees. So it is located at the fourth quadrant. So how does it looks like in the phasor diagram? So the phasor diagram is like this. Okay, for the third input. And what about the fourth input? Last, and then we can finish. Okay, the last one. Actually, we have 8. We have 8. So I just show you up to 4 input, 4 different inputs. I hope you understand about this. So you see that now the input is 0, 1, 1. Okay. So I channel is produced for the first 2 to 4 converter produce positive 1.307. Which is 1 and 1. If you see here is for the I channel, it is 1 and 1. 1 and 1 is actually for the fourth row, positive output. And for the Q channel is 0 and 1. 0 and 1 is negative 1.307, second row. Okay, so I channel multiplied with sine omega ct. Q channel multiplied with cosine at the product modulator, and the output of the linear summer is summation of sine and cos. So you see that it is positive sine and negative cos again. So positive sine, negative cos, so it is actually somewhere in the fourth quadrant. But how much is the magnitude? The magnitude would be summation of square root, summation of quadratic, and then square root. So we get 1.848 volt. What about the phase? Theta theta is arctangent 1.307 minus divide with minus 1.307. So we get 45 degree. So rewrite the equation to simplify the equation for the output of the linear summer. It is the magnitude sine omega ct minus 45 degree. And if we look the phasor diagram for the fourth input, which is located over here. Okay, so this is actually 45 degree. And this is 100 negative minus 135 degrees. Okay, so you see that we have seen, if we see the constellation diagram, the first symbol, second symbol input, third input, fourth input. And we have another input, another 4 input located on the second quadrant and the first quadrant. Okay, that is for the next 4 input, which you can try on your own. Similar with the phasor diagram, we have another, this one. So you see that this is for the 3-bit. Imagine if you have many bits. So we're going to have many constellations. So the idea is constellation is that we want to see the location of the symbols. Again, if the symbol is close one another, the chances of error going to be much higher. Okay, and you see that the output truth table, so this one, we can rewrite again the output truth table where we put the another column over here, the amplitude, the magnitude, which is the magnitude, and also the resulting phase, okay, that we have calculated previously. So I have shown you up to 4 different input. You can try the next 4 input for yourself. Okay, and this is for 16 QAM. This is you can try on your own. If we have a 16 QAM, 4-bit, it becomes like this, more complicated. Okay, this is for 16 QAM or 4-bit, where we have Q channel and Q prime channel, I channel and I prime channel. Okay, so you can try this on your own. Okay, and that's it for today, for tonight. Sorry to take longer time. I take half an hour of your time. So now maybe you can open your QR code reader and you can scan your attendance. Okay, you can scan your attendance and then you can do whatever you like. Okay, so section 1, get ready. So I will start open for section 1. Okay, section 1. Okay, attendance, section 1. Okay, thank you. See you again next week. Okay. Section 2 after this. Okay, section 2 after this.
Thank you, Doctor.
Okay, welcome.
Thank you, Doctor.
Okay, welcome.
Thank you, Doctor.
Okay, welcome.
Doctor.
Yeah.
Thank you, Doctor.
Okay, welcome. Okay, quickly, section 1. After this, section 2. Cepat sikit. Section 1, scan.
Done.
Okay, thank you. See you again.
Thank you, Doctor.
Okay, welcome.
Thank you, Doctor.
Okay, welcome. Any more? Section 1. 1, 2, 3. Okay, done Section 1.
Doctor.
Okay,
Doctor,
ya.
Doctor.
Siapa lagi?
Doctor,
Cepat.
I can scan it. I can scan it.
What's your
Muhammad Nur
name?
Hakim. Muhammad Nur Hakim.
Muhammad Nur Hakim. Okay, done. Any more?
Afiq. Ni Afiq.
Saya doktor.
Ni Afiq.
Ni
Muhammad
Afiq.
Hakim. Muhammad
Ni
Hakim.
Muhammad Afiq.
Ni Afiq.
Okay. Okay.
Muhammad Hafiz bin Isa. Saya doktor.
Hafiz Isa. Okay, done. Any more? Okay. So now section 2 so we go to section 2. Okay, section 2 you can scan. Okay, see you again next week.
Thank you, Doctor.
Okay, welcome.
Thank you,
Thank you, doctor.
Okay, welcome.
Thank you, Doctor.
Excuse me,
Okay,
doktor.
welcome. Okay, welcome.
Doktor, nama saya tak boleh scan. Siti Aisyah.
Tunggu sekejap. Tunggu sekejap.
Thank you, Doctor.
Okay, welcome.
Thank you, doktor.
Okay, welcome.
Doctor.
Okay, welcome.
Thank you, Doktor.
Okay, welcome.
Doktor nak tanya soalan
Okay, boleh tanya.
yang just now doktor yang ajar QAM kan, adakah dia akan gabung yang sebelum ni punya macam yang last week kita belajar kan? So contoh doktor kata untuk final kita dia akan keluar 16 bit right? 4 bit. So 4 bit.
Tak. Tak, yang final exam is up to PCM for the quantization. Not this QAM. QAM is not going to be in the final exam.
Final exam. Okay.
Yeah, the one that I mentioned in class is actually referring to the quantization, which is up to 4 bit, okay, where you're gonna have 16 levels. 2 power of 4 is 16. But that one is for quantization. The one that we learned tonight is actually for QAM. QAM is for the digital radio transmission. If we do the modulation with analog carrier, it's a different thing. Okay.
Okay, doktor.
Okay.
Thank you.
Okay, welcome. Siapa tadi yang tak dapat scan?
Excuse me, doctor.
Yeah.
I can't
Your name?
scan my Muhammad
Doctor?
TK Miklid.
Pardon? Your name is Muhammad?
Muhammad TK Miklid.
Okay, TK Miklid. Okay, done. Who else?
Okay, doctor.
Bashar. Sekuarasan.
Okay, wait. Bashar. Okay, done. Who else?
Kuarasan.
Ahmad Amin.
Siapa nama? Puvarasan.
Ya, betul.
Okay, done. Who else?
Siapa
tadi yang siapa tadi yang student perempuan? Student perempuan tadi siapa nama?
Saya Doktor Siti Aisyah Yusof.
Siapa nama?
Siti Aisyah Yusof.
Oh, tadi section tadi
Section 1.
Okay, tunggu sekejap. Section 2 siapa lagi? Who else? Section 2? Quickly.
Aziz Hazan.
What's your name?
Aziz Hazan. Number 4.
Aziz Hazan. Okay, Aziz, done. Okay, who else? No one? Tak ada Okay, sekejap. Tadi siapa? Siti Aisyah tadi. Siapa nama?
Betul.
Siti Aisyah.
Saya Doktor.
Ya. Siti Aisyah. Okay, done.
Doktor.
Okay, welcome. Siapa lagi?
Amin Amri.
Section berapa?
Section 1.
Ahmad Amin Amri. Okay, done. Okay, dah.
Terima kasih.
Okay, sama. Any more?
Doctor, I'm Hamad.
So you are section 1 or section 2? Section 2, right?
I'm section 2, yeah.
Your name is? Hamad.
Hamad Isa.
Okay, Hamad, done. Ada lagi? Who else?
Not done, doctor.
What's your name?
My name is Hamad Isa.
Hamad Isa, done. Yeah, Hamad Isa is done.
All right. Thanks, doctor.
Okay, welcome. Who else? Siapa lagi? Ada lagi? 1, 2, 3. Okay. That's it.
All right. Excuse me, Dixon.
Yeah.
Just I have an inquiry for our project.
Okay.
Actually, we need to play the audio after receiving the signal, right?
Yeah, you need to play the audio and then you pass through the transmitter and then send to the receiver.
Okay, but we have like a problem that we are cannot to play the audio.
So what input you have? You need to have the input.
Is it that is maybe because the type of the speaker, or
normally we connect with the audio jack. Okay, normally we have the audio jack. We connect to the input, and the audio jack we connect with our mobile phone. So mobile phone we use a mobile audio jack connect to the transmitter. So the transmitter will transmit the signal to the receiver.
okay?
So you need to think about what you can do for the input. If you use a speaker, that means you need to speak every time, which is difficult. My suggestion is to use the audio jack. Okay.
Oh, okay. Yes. All right.
Doktor
Okay.
nak tanya,
Thank you.
Okay.
dekat receiver tu kan doktor nak keluarkan sound daripada input kan?
Okay.
Kalau guna sound tu keluar guna earphone boleh ke?
Boleh. Yang penting kita boleh dengar lah.
As long as dapat bunyi sound tu lah kan?
Ah, yeah.
Okay, thank you
Sama ada
doktor.
you nak guna speaker atau you nak guna audio jack earphone tu boleh juga. So that means kita boleh dengar lah. Kita boleh dengar apa tu? Contohnya you pasang music, kita akan dengar benda yang sama lah. Okay.
Okay doktor.
Okay.
Thank you doktor.
Okay, welcome.